All right, so then our last kind of symmetry here is symmetry about the origin. So this is where we had our symmetry in diagonal quadrants, reflecting over that point 0, 0. So this time, if we're in diagonal quadrants, thinking about like the first and third quadrants we used as our example. In the first quadrant, x and y are both positive. In the third quadrant, x and y are both negative. So we are changing both x and y when we reflect across the origin. So we are replacing x with negative x, and we're replacing y with negative y. So we're going to be changing both variables this time to check for origin symmetry. So that y will become a negative y, so we'll have negative y equals, and then we'll have the cube root of negative x this time. All right, and now we're ready to simplify. So starting with the cube root of negative x, remember that negative sign just excuse me, represents our coefficient of negative 1. And when we take the cube root of a product, so this is really negative 1 times x inside, right? We can split this up into the cube root of negative 1 times the cube root of x. And the reason I want to do that is because we can simplify the cube root of negative 1. We can get rid of the cube root there, but the cube root of x is not going to simplify. So that cube root of negative 1, a cube root just means we're trying to figure out what number do we multiply by itself 3 times to give us negative 1. And negative 1 times negative 1 is a positive 1. And if we multiply by a negative 1 a third time, that turns it back into a negative 1. So this cube root of negative 1 is just negative 1. But the cube root of x, since that x just has an exponent of 1 on it, there's not any simplifying we can do there. So that's just going to stay the cube root of x. So we were able to simplify the cube root of negative x to be negative 1 times the cube root of x is equal to negative y. And then our final step, we do want that to be a positive y, not a negative y. So we can do that by dividing by negative 1. And when we do that, our y becomes positive. And then on the right side, we also have a negative divided by a negative, which becomes a positive. So this becomes a positive cube root of x, which again is the exact equation we started with. Those two match. So that tells us that the equation y equals the cube root of x is symmetric about the origin. So again, when you're checking for origin symmetry, you change the sign of both the x and the y. And again, we can check for origin symmetry using an ordered pair as well, which is oftentimes a lot easier than just dealing with the variables. So they have graphed the cube root of x here for us. And again, they've provided us with some ordered pairs. And we are going to use the point 8, 2 as our checkpoint here. And again, we could have used any ordered pairs off of that graph. We're just choosing 8, 2 for this example. So if we're checking for origin symmetry, we change the signs of both of those. So we'll be plugging in a negative 8 for x and a negative 2 for y. And if when we plug those in, we get a true statement, then our equation is symmetric about the origin. There's a little bit of a mistake here. That should not be an x equals, just y equals the cube root of x. All right, so let's plug in our x and y values. So instead of y, we're going to plug in negative 2. Instead of x, we'll plug in negative 8. So simplifying the cube root of negative 8, just like we did earlier, we're thinking about what number do we multiply by itself 3 times to give us negative 8. And 2 is a number that when we cube it, it gives us positive 8. So if we made it negative 2 times negative 2 is 4. Multiply by a third negative 2. 4 times negative 2 gives us that negative 8 we have inside our cube root here. So the cube root of negative 8 is just negative 2. So we're left with the statement negative 2 is equal to negative 2, which is a true statement. So because we were checking for origin symmetry and we were left with a true statement, that means this equation is symmetric about the origin. Now origin functions, or origin symmetry, functions with origin symmetry, I should say, are functions. So these are what we call odd functions. And just a way to remember this, origin starts with O, odd starts with O, so those are the two that go together. Origin symmetry is an odd function. And then just to review, we said y-axis symmetry were even functions, and then x-axis means they are not functions, so they are neither even nor odd. Now we will come across some equations sometimes that can have multiple kinds of symmetry, just depending on how they are situated on the coordinate grid. And I do specify equations and not functions because specifically if a graph has x-axis symmetry paired with either y-axis or origin symmetry, then it is not a function. So there are common graphs. For example, we see here a circle that you'll come across a lot, especially like in pre-cal, or if you were to go into calculus or some higher level math, you'll come across circles all the time, but they are not functions. So there are equations, there are certain kinds of graph that do still have symmetry to them, they're just not functions. So we're going to use this equation of a circle, x squared plus y squared equals 25, and we're going to check to see if or what kinds of symmetry this circle has. And again, it could have multiple symmetries, it could have no symmetry. We can kind of make some guesses based off the graph that we're seeing. It looks like it's probably, if we focus on the y-axis here, we can see the same half of that circle on each side of the y-axis, so it probably has y-axis symmetry. So when we check for that, that should give us a true statement. If we focus on the x-axis, we see we have that same curve above and below the x-axis. So again, this looks like it probably has x-axis symmetry, so that's what we should expect when we check for it. And then across the origin, again, we can see that same curve on each side of the origin. So really we're expecting all three of these tests to give us true statements, because from the graph it looks like a circle does have all three kinds of symmetry. So they've given us a point off of this graph, 3, 4. So we're going to use that example point from our graph here to check for our three different kinds of symmetry. So with x-axis symmetry, this is when we change the y value. So we'll keep the x value the same, but we will change the y value to a -4. This is what we're going to plug in to see if our graph has x-axis symmetry. So we'll plug in 3 for x and -4 for y, and then we'll simplify. So 3 squared is 9, 4 squared is 16. So then if we simplify, 9 plus 16 gives us 25. 25 equals 25. So this tells us that because that was a true statement there, this graph does have x-axis symmetry. So then we'll check for y-axis symmetry. Across the y-axis is when we change our x value. So now we're going to change x to be -3, but we'll keep y as +4. All right, so we're going to plug in a -3 for x this time, but we're going to go back to +4. And then we'll simplify. So -3 squared is 9, 4 squared is 16, equals 25. And be careful here when you're squaring a negative. Remember, a negative times a negative is a positive. So then on the left side there, 9 plus 16 is 25. So we're left with 25 equals 25. Again, that is a true statement. So that means this graph also has y-axis symmetry. So we said yes to x, we said yes to y. Let's check for origin. Now across the origin, this is where we're changing quadrants diagonally. So both x and y are switching signs. So this will be a -3 and a -4. So we'll plug in a -3 for x and a -4 for y. But again, we're still squaring these values, and when we square a negative number, we do get a positive. So it's a positive 9 plus a positive 16. And 9 plus 16 still results in 25, so we are left with 25 equals 25, which is a true statement, which means our graph also has origin symmetry. So our graph this time was symmetric about the x-axis, the y-axis, and the origin. So this is an example where multiple symmetries show up. In this case, this is not a function, which is okay, so we're not going to classify this. With the type of function, we're just going to talk about the symmetry here. And because this circle was centered about 0, 0, this circle does have all three kinds of symmetry over the x-axis, over the y-axis, and over the origin. So there's just this nice little table here at the bottom of this notes page to kind of help you remember which symmetry you're looking for, how do you change your ordered pairs. And ordered pairs, I think, again, are going to be the easiest way to check for symmetry. So if we're checking for the y-axis, we switch our x values. If we check for the x-axis, we switch our y values. And actually, let me fix this. This is wrong. Here for y-axis, it says if xy, then x negative y. This should be negative x, y. For x-axis, that's where we change our y value, just change a sign, and then for origin symmetry, we change the sign of both x and y. And then remember, for type of function, y-axis is what we call an even function, origin symmetry is what we call an odd function, and then x-axis, because that is not a function, it is neither even nor odd. So feel free to review this video, watch it as many times as you need to. There are some extra examples worked out in the notes key, just so if you want some extra practice checking for types of symmetry and identifying types of functions, check those on Canvas. And feel free to ask your teacher if you have any questions about this.